Hello, I'm Dr. Azal from medicovisual.com, and in this visual lecture we will discuss the Henderson Hasselbalch equation. And I'm not gonna throw the equation on your face, but in this lecture we will actually learn how this equation, from where this equation comes from, and how exactly is this derived, how exactly this equation is derived. So we will learn from the very base. So without going deep into mathematics and chemistry of this, so we will start from the very basic concept. In the last lecture we had seen how the buffers work, the pH buffers work, and basically the idea of pH buffers is that when a weak acid, let's call this weak acid Ha, when it dissociates, it converts into H positive and OH, not OH, sorry, A negative. Now, if we add more of this A negative such that they become almost equal or nearly equal, this one and this one, then we will have this base fighting soldier, this one, and this acid fighting soldier, this is the conjugate base, which is the acid fighting soldier. We have discussed all those details in the last lecture. Now let's suppose that this hypothetical acid, it is being dissociated into proton and its conjugate base. Again, I will not go into these details, we have discussed this already in the previous lectures. So what will happen now? Actually, what if I tell you that for any reaction, I will go little bit in the chemistry, for any reaction, the more the number of reactants, more will be the rate of its reaction. Let me tell you what I mean by this. So let's suppose that we make a graph of energy. Okay, basically it's called free energy, and again, I do not want to go into too much complex details, but let's suppose this is the energy of let's say reactants. Again, this is energy, and this is the energy of, let's say, products. It should be spontaneous reaction, but to make this to undergo to for the spontaneous reaction to undergo, actually the reactants must cross a barrier like this, and then they need to be energized, and then they can do this reaction and form the product. And this is basically the activation energy. Now there is in some reaction there is some role of enzymes here, right? But we will not go into enzymes at this lecture. What actually happens that reactants may collide with each other, right? Reactants may collide with each other spontaneously. They may collide with each other, and then they may get more energized. So more the collisions, more frequent the collisions are, more energized will be the reactants, and more will be the rate of reaction. So what I mean by this, for example, here is the one reactant, here and another molecule of reactant, and so on. So basically they are moving freely like this, randomly in a haphazard fashion. So they may collide with each other, and as they collide with each other, they may get energized, right? So now I have a question for you, that if we have two containers, this is one container in which the concentration of reactants is very high. So many reactants are there. And here we have another container, and here the concentration of reactants is low. Out of these two containers, in which container the collision will be more frequent. This is, let's say, container 1, this is container B. In which container the collisions will be more frequent? So I hope your answer would be container A, this one. And because here more collisions will be there, it means that the concentration of reactants is higher in this case, right? And there will be more collisions. It means more of the reactants will quickly cross this barrier. They will reach the activation energy, and it means that more products will be formed. Now, to understand this more visually and more logically, I have created a simulation in Blender using geometry nodes. So here you can see we have this container in which the concentration is very low here, and here we have concentration is very high, and you can see already some of the reactants are so close to each other that they have already collided with each other and they got energized. So you see, I am assuming that when they collide with each other, basically their color changes to red. So if you look here, you will see very quickly most of these, their color changes to red in this container, the right one, and on the left one you see many of them, they are not yet energized. You see, after a long time has passed, now you see all of them here are energized enough that they can form the product. But here on the left hand side, because the concentration of reactants is low, it means many are still not energized. So what we can infer from this? So what we can infer from this, the thing is that if we talk about rate of reaction, this rate of reaction is directly proportional to the concentration of reactants. It means more reactants in per unit volume. Let's suppose here per unit volume we have more reactants as compared to this one. If we have more reactants, it means the rate of reaction will be high. So actually there is a constant of this. If we write it in terms of equality, we can write it rate of reaction is equal to some constant and multiply by concentration of reactants. And this constant, it is some internal inherent property of that specific reaction. I hope you get the point. And of course it also depends upon the environment, but we will not go deep into the chemistry. Now the thing about the weak acid is that they they never completely go into completion. What I mean by this is that, let's suppose we have 10 molecules, just for the sake of understanding, it is not that low. 10 molecules is incredibly low. So let's suppose we have 10 molecules. It does not mean that all of the 10 molecule will be converted to this and this and this will become zero. No, it won't be like that. It will never be like that. Suppose we have 10 molecules here, maybe only 1 or 2 may be converted into this, but other might go actually back. What happens actually when we add more what is this one or this ion, then this reaction might go back, right? Okay, let me tell you in another way. I know some of you might be confused, so let me draw this equation. Let's write it again. HA and H positive plus what is this, A negative, right? So let's suppose that initially we have 10 of this and 2 formed here, 2 formed here. Now let's suppose we add 10 molecules more here and they become 20. So after some time, following the same ratio, this should become 4 and this should also become 4. Now what actually happened that after some time, Some of these they may start to go back. For example, for momentarily, like this might become 3 and this might become, let's say, 19, but then immediately one will jump here back and this will become again 20 and 4 and 4. So basically there might be some backward reaction, but the rate of forward reaction as well as backward reaction after some time will become equal. So this is why we write it like this, a reversible reaction, that there is some forward reaction F and then there is backward reaction, and these are at the equilibrium. After some time there is a state of what we call as dynamic equilibrium, where both of these rates they become equal. So what we can write it in a way that actually we can replace it with this constant, with kf. This is forward constant, and here we can write kf, and then this one is backward constant, or we can write it symbolically in a more traditional way like this, as you see in your textbooks, kf and kb. Now what happens that at the equilibrium constant rate of, okay, first write what is rate of forward reaction. What is the equation of rate of forward reaction? That is kf multiplied by, what is this? These are the reactants for the forward reaction, and these are basically HA. And if we go backward, let's suppose actually we can add this ion, and this might go backward. So for that rate of backward reaction, if we write the equation of rate of backward reaction, we can write Kb into that. What are the reactants here? These are the reactants here. So we can write it like this: H positive and A negative. Now what happens at equilibrium? What happens at equilibrium? At equilibrium, rate of forward reaction is equal to rate of backward reaction. So now if we put the values of these equations here, so this will become kf. Actually we can just ignore these cross or multiplication sign. We can simply write it like this. If you know mathematics, it means the same basically. So we can write it like this: H positive and A negative. Now actually we can do something here, that we can divide this one by, okay, let me show you. We can divide it by kb on both sides. We can do it in maths, you know. We can divide by kb on both sides like this. This will become, these two will cancel out, and then we can write it like this: kf over kb into HA. I hope you are not confused. Very basic knowledge of maths is of course required, basic algebra, but I do not expect you to be very advanced in mathematics to understand this. Okay, so then we can rearrange the equation, but I do not want to confuse you, so we can. But before that, let me tell you something. This kf over kb, this is actually a constant, and for acid we call it Ka. So kf over kb is the dissociation constant of acid, which is called Ka. Now Ka, it depends upon the strength of an acid. If acid is strong acid, it means that this forward reaction will be very high. The rate of forward reaction will be very high as compared to backward reaction. So this Ka will be high for a strong acid and it will be low for a weak acid. But anyhow, we can substitute it here. We can write it Ka into Ha, then H positive and A negative. Now here again we can divide by A negative. Why we are dividing by A negative? Because we want the value of H positive, and in this way we can get it. Let me show you how. So these two will cancel each other, and now we will have equation like this over A negative is equal to H positive. Or we can reverse it. Basically we can also write it like this: H positive is equal to Ka, the dissociation constant, into Ha, which is concentration of acid, divided by A negative's concentration, which is concentration of its conjugate base. Now actually we want an equation which we can use to calculate the pH of a weak acid as well as the pH buffers. So from this concentration of proton, the concentration of H positive ion, if we take negative log of this, we can get the value of pH. But we cannot simply take a negative log here and ignore this thing. We need to take negative log on both sides. Take negative log on both sides of the equation. Both sides of the equation. So we can write it negative log H positive is equal to negative log of whole this thingy, like this. Now can I write it like this? Of course we know this is equal to pH, so we can simply substitute it with pH. Now can I write it like this: negative log of Ka multiplied by negative log of Ha, concentration of Ha over A negative. Can I write it like this? Well, actually no, this is not Henderson Hasselbalch equation. We cannot write it like this. Let me show you why we cannot do this on the side. So I will not go again into what is the log. We have discussed it in the lecture of pH. But a very basic idea that I would like to give you here, that let's suppose we have a number like this: 10 multiplied by 10 multiplied by 10. How many zeros are there? 1, 2, 3. We can multiply it like this and we can get 3 zeros. Now we can also write it like this, that this is 10 raised to power 3. So 10 multiplied by 10 multiplied by 10 is mathematically equal to 10 raised to power 3. By definition, 10 raised to power 3 means 10 multiplied by itself 3 times. So if we take a log of this value, take a log of 10 raised to power 3, or we take a log of 1000, or we take a log of 10 multiplied by 10 multiplied by 10, it does not matter. We can also write it like this, or we can also write it like this. We can also write it like this. Now it is basically equal to 3. So very simply put, in a very simple terms, log is basically counting this number of zeros. So 1, 2, 3 zeros are here, so we have log 3. Now you can do this experiment for the simple terms. Let's suppose I write it 1, 2, 3, 4, 5 zeros, and I take a log of this number, then this will be 1, 2, 3, 4, 5. This will become 5. You can do this on calculator and check this. Now let's suppose I have a value like this. Okay, let's suppose I have a value like this, 10 raised to power 3 multiply by 10 raised to power 2, and these are in brackets, and we want to take a log of whole this value. Now we can do two things. Let's write first the wrong way. We can we write it like this, log of 10 raised to power 3 multiply by log of 10 raised to power 2, the way I did it here, like this. Can we do this? Let's check this out. Okay, so log 10 raised to power 3, as I've told you, its value will be 3. You can check this on calculator, and this value will be 2. If we multiply this, the answer will be 6, and we will see if this answer is correct. Or the other way is that we can write it like this, log 10 raised to power 3 plus log 10 raised to power 2. Okay, let's calculate this one. Its value will be 3, and this one, its value will be 2. So 3 plus 2 is equal to 5. So which one is correct, this one or this one? Well, to really check this, we can do another thing. Let's solve this one in another way. Log 10 raised to power 3 multiplied by 10 raised to power 2. We can write it log, okay, we can write it like this, 10, we can write it like 1000, like this, and we can write it multiply by 100. So this will become 1 2 3 4 5 4 5, and when we take the log we will have 5. So basically we are counting zeros, and it's again a rule in mathematics that when we multiply these powers like this, we have to add it. So in another way, I can say it like this, that 10 raised to power 3 multiply by 10 raised to power 2 is basically equal to, write it like here, basically it is equal to 10 raised to power 3 plus 2. So it is basically equal to 10 raised to power 5. So that's why this solution is correct. We can, if we have multiplication sign like this and we want to simplify it, we have to replace it with positive sign. We cannot multiply the answers to the log like this. So that is why this one is wrong. We have to, if we want to expand it, we have to write it like this, negative log of k positive, not k positive, ka, right? And then we cannot multiply, we have to write plus, the reason I have told you. Then we have to write like this, negative log. It's a basic rule of logarithm. The reason I have told you, I hope you are still not confused. If you are, I think you need to go much deep into mathematics to understand this. Even I don't know the nitty-gritty details of the maths behind it. So negative log of Ka, this is actually called pKa. So we can actually replace it with pKa, and then again there is a rule in mathematics that if we multiply plus with minus numbers like this, in this condition we will have to write it negative. We can simplify it, we can open up this brackets and we can write it like this, HA over A negative. Now some scientists, they do not like this negative value. Even this equation is complete actually, but some scientists, they do not like this negative value here, so they want to replace it with positive value. So to do this we can actually flip this, and this time I won't tell you how it works. You have to figure it out yourself if you want to, but we can flip it like this, and this is exactly equal to the equation above. So both of these equations are exactly equal to each other, and this is now the final equation. and this equation is called Henderson Hasselbalch equation. This equation is called Henderson Hasselbalch equation. This is used to calculate the pH of weak acid, and by that we can also use it to calculate the pH of buffers. So let's create a titration curve of an acid. Again, we will still go into a fictitious acid for now, but later on I will tell you some real buffers, the pH of some real buffers as well, but we will go into that a bit later. So let's suppose that I have a beaker. We have two beakers, let's say. And in one beaker, let me first create the two beakers. So in both of the beakers, we have exactly equal amount of buffer here as well as here. So we have same buffer, and here also we have similar configuration of the buffer, and here also we have similar initial configuration and initial pH of the buffer. Now here what we do is that we start putting little by little, drop by drop, we start putting the, what is this, a very strong acid here. Let's suppose HCl. Few drops of HCl we put here, right, and we can control this. This is called titration. You might have done these experiments in your chemistry class, actually, in the secondary school, in the college. So here in the other situation we are adding a strong base, and again we can calculate it. We can control it using this thing, right? So now in both cases, first we will talk about acid, then we will go into this base thing. So initially, what is the initial situation? Initially, let's suppose we have the HA and we have A negative, and we can also write pH. Now initially, let's suppose we have 0.04 unit of acid and 0.04 unit of its conjugate base. What will be the pH? Let's suppose for this fictitious acid, the pKa is 6.1, let's say. To calculate the pH, we know this equation, this one. So if we put it in this equation, pH is equal to what is this, pKa plus log A negative over HA. Now what happens here? Let's put the value. Let's suppose for this weak acid, its value is 6.1 plus log and 0.04 over 0.04. This will be 1, and log of 1, you can do it on calculator, it will be 0. So pH will be equal to pKa. When these ratios are equal to each other, that will be equal to pKa, and that value is 6.1. So initial value is, let's suppose, 6.1. Add that initial value here, also initially 6.1, here also initially 6.1. Let's say we also added a pH meter here. We can also do this, but rather I think for this I will use the equation to calculate it. Now let's suppose we do something that we add initially, let's say 0.005 units of this strong acid. Okay, let me show you. Okay, 0.005 of HCl, let's say we add here, then as I've told you, it's a strong acid. It will completely dissociate, almost completely dissociate into H positive plus Cl negative. It means that if we added this much, after some time this will become 0 and all this will be 0.005 of this and 0.005 of this. Okay, let's make it bigger for the sake of simplicity. Let's say we add initially 0.01 unit, not 0.05. So our calculation become a bit faster. So initially here there will be 0 0. After some time this will become 0. HCl will become 0. It will be completely transformed into 0.01 of this and 0.01 of this. This won't be doing much here. This is the thing of our interest here. Now this 0.01 unit of H positive, it might increase the, not increase, it might decrease the pH drastically, but fortunately we have this conjugate base in our buffer solution. So what this conjugate base will do, let me show you the equation again. Ha over, right, like this, H positive plus A negative. Now what it will do is that this A negative, initially let's write it 0.04 and 0.04. Let's ignore the value of this for now. So what this one will do is that it will pick up this proton, this one, the external proton. And how much is the amount? 0.01. So it will react with this much proton and it will be converted into this. So it means that this much proton, almost all of, not almost, actually all of this will be converted. It will react into this and it will, this value will increase. So after some time what will happen, that it will become 0.05 and this one will become 0.03, like this. I hope you understood what actually happened here. If you watched my previous lecture on the buffer solutions, you might understand what is going on, that this conjugate base, it is the acid fighting soldier. It will quickly pick up this proton. Then it will be converted into, it will go back in the backward reaction and it will be quickly converted into Ha. Now in reality, this increased Ha will also form a little bit more of this ion, this internal ion, the self dissociation, that's what we call it. But for the sake of simplicity, we can actually ignore this, especially when this ion is high. This process is actually reduced, the self dissociation is reduced. If you want to go deep into this, you can go and read the Le-Chatelier principle, but I do not want to go into that. So the idea is that for the Henderson Hasselbalch equation, it is not absolute true value, it is actually approximation, a little bit of approximation. But anyhow, this was something that I wanted to mention, but I do not want to go into detail. Now let's say if we add 0.01 unit of acid, so it means that this 0.01 unit of acid will increase this Ha by 0. This will be added here, so 0.04 plus 0.01, it will become 0.05. This will increase a little bit and this will decrease a little bit. Why it has decreased? As I've told you, that it will be reacting. These soldiers are unique, that when they fight with the acid, they do not die, but they become the other type of soldier. They become the base fighting soldier. I hope you got the concept. If you watched my previous lecture, I'm damn sure that you won't be confused by now. But anyhow, again, we can use this equation to calculate the value of pH plus log. Here we can enter the value 0.03 over 0.05. Now I can use a calculator to calculate this. 6.1 plus now I didn't want to do all this manually, all this maths manually, so I used the power of Microsoft Excel formulas. It might look intimidating at first sight, but don't worry, it's very easy to understand. Let's suppose we start from here, from 0.04 units of conjugate base and 0.04 unit of the acid here, right? Then we gradually start adding the strong acid and its values begin to change. 0.01 unit of acid is added, so this value decreases. This one, the conjugate base decrease, conjugate acid, not conjugate acid, the acid, the weak acid, it increases. The pH changes, it continues, so on and on. And then after this 0, the now this is excess acid. Now all this acid, it will not be buffered, all the H positive ion, it will not be buffered. Rather, at this point we will directly use this value 0.02, 0.01. These are the value of H positive. They are not bothered by proton. We will use the negative log of these values directly. This is excess proton. We will use negative log of these values to calculate the pH. Similarly, then in the other beaker, as I've shown you in the diagram on the board, on the sketch pad, that on the flip side we can start adding the base, a strong base, and again the pH will change in the opposite direction. And if we plot the graph, we will have a graph like this. Now here let's suppose that pKa was 6.5 for this. So we started from here. By the way, when pH is equal to pKa, and okay, if we take a log of 0.04 over 0.04, hold this value, its log will be whole of this value will be 0. So when pH is equal to pKa, it means that ratio of conjugate base and acid is equal. So we started from this point. It will be somewhat here, 6.1, yeah, somewhat here. So we started from this point. Now here you see, from here if we go down, and we are adding more and more acid, so pH changes very little, until our base fighting soldier, not base, acid fighting soldier, I mean the conjugate base, it becomes very low and ultimately it is lost. Then suddenly pH drops, and here as well we have the base fighting soldier, that is the HA, the weak acid. It continues to fight with the coming strong base, but suddenly when it becomes very low and ultimately it becomes 0, then there is sudden spike in pH like this. And I will not go into this plateau here, there is some other reason for that, let's not go into that. But here you can see from pKa to point here, somewhat here, and here you can see that there is not very drastic change in pH between these 2 points. So basically pKa plus minus 1 unit, so if it is 6.1, so from about 5.1 to 7.1, this is the buffering range. Between this range, the buffering capacity is pretty good, but outside this range, there is still somewhat buffering capacity is still somewhat there, but it is not as efficient as between this range. So this was the logic of this equation, this graph, and this is, by the way, called titration curve. Let me tell you in another way that we can also start from a weak base. We do not need to start from the center. We can start from here, let's suppose, and we begin to add a strong base, and then again we will get a curve like this, right? Or we can start from this point and then we begin to add a strong acid, again we will get a curve like this. So it does not matter. Practically, in chemistry practicals, what we actually do is that we start from a weak acid and we begin to add the strong base into it, let's say NaOH. We do not do like this, that we divide it into two containers and in one container we add acid, in another container we add base. That is more of a pedagogical point of view, that is more from the pedagogical point of view, but not from practical point of view. The practical in chemistry practicals, I have told you how it's done. Now, one of the most important buffer of our body is the bicarbonate buffer. It is H2CO3 and it converts into H positive plus HCO3 negative. Now, the pH of our blood is 7.4 on an average. It is 7.4. Actually, it's a range 7.35 to about 7.45, but on an average we can take this value. Now, at this value, the pKa of this acid is this acid is 6.1. Now, what will be the ratio of these two things at the blood pH? Let me show you something very interesting here. So, let's come back to Henderson Hasselbalch equation. pH is equal to pKa plus log A negative over HA. We want to know this ratio. So we can rearrange this equation. Okay, let's first write the values. 7.4 is equal to pKa is 6.1 plus log of this A negative over HA. Then we can write 7.4 minus 6.1. We can bring this value here, so we will have to subtract it here. Then log of this A negative over HA. Then what will be this value? I will use calculator. 7.4 minus 6.1, 1.3, and is equal to log A negative over HA. Now we can take anti-log here, and to take anti-log we can simply take power of 10 like this, 10 raised to power 1.3, and here again is equal to 10 raised to power hold this value. If we take anti-log, if we write it like this, A negative over HA, then this will become like this, 10 raised to power 1.3 equal to A negative over HA. Why it is so? For that again you will need to go into log, and I do not want to do that again. I hope you understand by now. So we can calculate it, 10 raised to power 1.3, so it is 19.95, almost 20. So actually this ratio is 20:1. That's interesting. So it means that at the pH of blood, we will have about 20 molecules of A negative conjugate base, not A negative. I should actually write it like this, and here as well, but I will just write it here, HCO3 negative. And here I should write H2CO3 like this. So it means that we will have, if we have 20 molecules of HCO3 negative, we will have 1 molecule of H2CO3. This HCO3 negative, the bicarbonate ion, is the acid fighting soldier. It's the conjugate base, it's the acid fighting soldier, and this one is the base fighting soldier. It means for this very important buffer of our body, we have much more acid fighting soldiers as compared to base fighting soldier. We have very few base fighting soldier, we have much more acid fighting soldier, and that makes sense because mostly we have much more acid that is being produced in our body as compared to base. So it is well equipped and well efficient in fighting with the acid as compared to base. It can neutralize more acid load as compared to base load. And let me show you practically this thing as well. Okay, let's go again to Excel, and we will write the formula. Let's suppose that what is the normal blood pH? Normal blood pH is 7.4, and let's suppose we add 0.5 units of acid, and let's see how much pH changes. And to do this, we will use the formula, the Henderson Hasselbalch equation, 6.1, which is pKa plus log base 10, or we can simply write log of A negative. A negative is bicarbonate ion. So bicarbonate ion, at blood pH we have 20. So if we add 0.5 unit of strong acid, so we will have 0.5 deducted from here like this, and we will have 1 unit added like this here. Oops. Okay, and yeah, we can write the formula like this. So if we add 0.5 unit, this will be the pH and of the acid. So if we add 0.05 unit of base, then what will happen? So if we add this base, then what will happen, that again 6.1 plus log, and now which fighting soldier will take part in this action. So on the top, on the numerator, we have the 20, which is the bicarbonate ion. So now if base is added, bicarbonate ion will actually increase by 0.5, and the acid, the conjugate acid, will actually decrease because that is taking part in this fight, so that will increase. I think I did something wrong here. 6.1 plus log 20. Yeah, I did minus here. It is divided here like this. Yeah. So how much change has occurred? Actually, to see the change, we can take a difference like this. We can, from 7.4, we can minus this value. So this is the difference. And again from 7.4, by the way, people who know Excel, They might be shouting at me that I can reference this cell like this. I know, but for non-technical people, I am explicitly writing it so that they can understand. Yeah, so 7, it's 7 minus 7. Okay, I can reference it like this, then minus 7.4. So this is the difference. So this is the pH change. So you see, when we add the same unit of base, we have relatively larger change in the pH, but if we add same unit of acid, we have relatively lesser change in the pH, and we can actually show it graphically. I can draw the graph. Yeah, we can show it graphically like this, that in this situation, when we add the acid, there is little increase in pH, but if we add a base, then there is more increase in pH. It means that this bicarbonate buffer system is much more equipped to fight with the acid load as compared to the base. So this makes sense. Although it is far from although it is far from the pKa, as I've told you, the buffer works best when it is closer to pK. The pH of blood should be closer to pK. So its pKa is 6.1, but we are outside the true range of its buffering capacity. Its buffering capacity is somewhat between 5.1 to 7.1, and we are actually outside this range. We are at 7.4, but still it works great, especially for the acids. Not very well equipped for the base, but it is well equipped for the acids. Now, besides this bicarbonate buffer system, this is the most important buffer system. We have other buffer system as well in our body, but before that, let me tell you something interesting. So for this buffer system, we have HCO3. Let's write its Henderson Hasselbalch equation again. 6.1 plus log HCO3 negative and H2CO3. Now actually we know the value of this. Okay, let's write it again. We know the value of HCO3 in our blood. Normally it is about 24 millimole per liter, this concentration, but we do not know, and we cannot calculate the value of H2CO3. We can actually calculate indirectly, but we cannot measure this value of H2CO3 from our blood. What I mean by this is that you cannot take ABG's arterial blood gas sample and then send it to lab and get this value directly, but we can indirectly calculate it. How we can indirectly calculate? Because it is proportional to the CO2 value of the blood. So in blood we can get the partial pressure, we can measure the partial pressure of CO2 gas, and partial pressure means that the pressure this gas would exert on the container if this gas was alone. If there was no other gas in our blood or in the container, the pressure that this gas would exert, the CO2 would exert, that will be its partial pressure. Now, if we multiply the partial pressure with the solubility coefficient, which is 0.03, we can almost get this value of H2CO3, but let me tell you, you can dive deep into this rabbit hole that it is not the precise value of the H2CO3. We do something with this one, we tweak this one to get this value precise, but again, I do not want to go into that. That's very complicated thing. 0.03, which is the solubility coefficient. We can replace this with PCO2. We can replace these values like this. So now we know, actually we know this value, and we can write it. This value is normally 40 mmHg, 0.03 into 40 mmHg. These are the normal values, and if we substitute and we calculate it, ultimately we will get 6.1 plus log 20, and if we calculate whole this value, we will get the value of pH as 7.4, which is the normal pH of our blood. So this was about the bicarbonate carbonic acid buffer system, or bicarbonate CO2 buffer system. We can also say it like this. This is very important buffer because this H2CO3, it is directly corroborated with CO2 levels, and the CO2 can be exhaled outside. So this is actually the volatile acid, that's what we call it. But besides that, we have some other buffers as well. We have phosphate buffers and we have protein buffers that I will not go into those details. And we have hemoglobin buffer as well that we have discussed in another lecture as well, but again this will come in the next lecture as well. I will discuss it briefly, but I think that was all for today about the pH buffers and Henderson Hasselbalch equation. Thank you so much for watching this video. Have a great day. Goodbye.